All right, thanks for the introduction. I'm Tal, I'm a PhD student at UCLA, and this is work with my advisor, Guy Vandenbroek. So we're going to be talking about discrete probabilistic inference here. So a good starting point for this is to talk about factor graphs. So factor graphs are a powerful representation tool. They can represent, your Bayesian networks, your conditional random fields, your restricted Boltzmann machines, that kind of thing. And factor graphs are really nice because they give you kind of this visual graphical representation of the key features in a joint probability distribution, which is the independence properties, right? So, this factor graph is showing us that the probabilities of A and B depend on each other, that B and C depend on each other. But if we know the value of B, then now we know that A and C don't depend on each other anymore. So factor graphs are nice, but ultimately what we really want to be doing with a joint distribution is asking questions about it, right? And in general, this is hard. So, for example, if we wanted to know the marginal distribution of A summed over all these other variables, this is in general a very difficult problem, right? So if we wanted to do exact inference, so to compute these probabilities exactly, what we would typically do is we would use what's called knowledge compilation. We'd build kind of an arithmetic circuit representing the factor graph. You may have heard of like a binary decision diagram or a sum product network. And then once we have that circuit, they're what's called this like tractable form. So basically this marginal and a whole bunch of other queries and manipulation operations, we get them kind of for free. And these circuits also have some kind of nice properties where when we're building them, we compact them by taking advantage of, kind of more subtle independence properties and sort of logical structure if it exists. But these circuits have kind of one problem, which is that they don't scale, right? We know just at a level, at a complexity level, we know that they're solving exactly a problem that's really hard. So we know that at some point we're just not going to be able to build this if you pick a factor graph large enough. So what we would like to do is we would like to take all of these benefits from knowledge compilation of having some exact inference, of taking advantage of these independence properties, but we'd like to also get kind of these nice benefits of doing sampling where it's scalable, it's anytime, it's, just give me as much time and resources as you can and I'll give you the best answer I can come up with. And what we'd really like is to kind of sit in the middle and take advantage of both of these things, right? Okay, so if we want to take advantage of some exact inference when we're doing sampling, the way that we typically do this is through something called collapsed sampling, or you may have heard it called Rao-Blackwell sampling. And the idea is that you do sampling on some of the variables, and then you do exact inference on the rest conditioned on that sample. So if we go back to our factor graph, maybe we decide that we're going to sample variables A and B, so we pick values for that. We observe those sampled values. And now we're going to compute exactly the probability of C given A and B. And we've made use of both. Okay, so this is kind of a powerful variance reduction technique. And it's pretty useful. But there's this very difficult question that it raises, which is which variables do we sample? Which ones do we do exact inference on? And I'd kind of even push that one step further and ask, like, is it always possible to pick a correct set ahead of time, right? And I'm going to argue that the answer is no. And to kind of get an intuition for it, let's consider an example, right? So we have a network of people, and we're interested in whether or not those people smoke. And now we know that friendship has an influence on kind of, if you're friends with someone and they smoke, you're more likely to smoke. And we've decided ahead of time that we're going to sample these friendship variables. And now, two different samples that basically look like factor graphs, right? If you take each of these edges as being kind of pairwise factors, you have a factor graph. And now the problem is that if I want to pick from here which variable to sample, there aren't really good choices for variables that will work in either case, right? Say I pick variable 1. In the example on the left, this is going to help us a lot because this is kind of a densely connected region, so it's going to make exact inference a lot easier. But in the example on the right, exact inference was already easy because this is a tree structure. And by sampling, really, all that we're doing is just introducing more noise. We didn't need to sample this. So what we'd really like to do is we'd like to do sort of an on-the-fly selection and say that, based on the result of sampling those previous variables, now we get to pick, right? So in our previous example, we'd like to be able to choose which variables to sample once we know what the friendships are. And we call this online collapse sampling. And we have a theorem in our paper that shows that you'll still get an unbiased estimator doing this. Okay, so we have this idea here. So what are the things, that we need to do to be able to actually implement one of these samplers? Like, how do we do it? So the first thing that we still need to do is to decide what and when to sample, right? We haven't solved that problem yet. We've just given us tools to make it possible for us to solve it. We need to decide how to sample, right? Because we can't assume in general that we can directly sample from the distribution of the variable. So typically what we do is something called importance sampling, where we say we're going to sample from a different distribution, call it the proposal. And then afterwards, we're going to correct for that to make sure that our estimate is still unbiased. And here, kind of the key is that the proposal needs to be fairly similar to the true distribution. But here, the problem is actually even harder because we need to have a proposal for any variable conditioned on any other variables because we don't know what order this is going to happen in. And finally, we need to be able to do exact inference, right? So before we saw that you need to be able to do exact inference on C conditioned on A and B. But now this is kind of taken a step further because we need to be able to do basically any combination. We don't know what we're going to wind up with at the end. Okay, so I'm now going to introduce the way that we do all these things, that we implement our sampler in what we call collapsed compilation. So the idea here is that we can go back and forth between doing exact inference and sampling. In our exact inference phase, we basically use knowledge compilation. We incrementally build a circuit that represents the factor graph. We go kind of factor by factor. Whenever the circuit gets to be too big, we move to our sampling phase where we kind of pick variables to sample and then pick values for them. And whenever the circuit is again small enough, we go back to doing our exact inference. So we continue doing this until we've considered the entire factor graph. And now what comes out of it is a circuit representing the factor graph where some of the variables have been sampled. Okay, so let's revisit those three questions and see how we're going to answer them. Right, so, well, what and when do we sample? So the when is chosen for us, right? We just kind of have to do it whenever the circuit is too big. And the what is, well, we're going to use a heuristic on the current circuit. And to give kind of some intuition for what you would want from your heuristic, if you have a variable that's kind of very densely connected to other variables, but it's not very strongly correlated in all of those connections, that's an example of a variable you really want to sample. That dense connection is going to make exact inference hard, but the weak correlation makes sampling really effective. And if you have the opposite situation, then that's an example of something you really don't want to be sampling. Okay, the next question is, how do we sample? So remember we talked earlier about how we're going to do importance sampling, so we need a good proposal distribution. So whenever we need to sample a variable, right, we have a circuit containing that variable and also containing a whole bunch of other information. But remember what we talked about earlier, right? These circuits are a tractable form. So all of these queries are easy, right? So we already have the circuit. So let's just compute the marginal of the variable in the current circuit and just use that as our proposal distribution. It's highly effective and we're getting it for free. And finally, there's the question of how do we do exact inference? And I mean, this follows in a pretty straightforward way, right? I said the result of doing this is a circuit with sampled variables. So just, run whatever query you need to on that circuit that you have. We know that any joint can be computed efficiently and exactly. Okay, so you've run this a few times, and now you have a bunch of circuits. And for each of these circuits, you have a weight, which is, how much attention should you pay to each of these circuits. Alternatively, you can also think of it as how likely was this circuit to happen. And you put all of these together. On each of them, you can compute, whatever query you want efficiently. And you use those together, and you can approximate whatever query you want. So to validate this empirically, we basically study exactly the problem that we've been talking about, which is, how do you compute a marginal in a factor graph? We're going to compare to a couple of other methods which use sort of this combination of exact and approximate inference, but in different ways. And to do this comparison, we're going to basically, at an algorithmic level, limit how much exact inference we're doing. so that we can have sort of a better comparison of how they're using it. So we find that basically pretty much across the board, but depending on exactly which configuration of example and heuristic you're using, you get results that are basically either comparable to or slightly better than the state of the art. Okay, so I'm about to wrap up here, but my kind of 30-second takeaway for if you dozed off at the beginning and you want to know what you should remember is that we have these tools for doing exact inference from knowledge compilation that are very powerful, that take advantage of a lot of nice properties, but we know that they don't scale. And we have these properties from our kind of normal toolkit of samplers, which let us sort of do the best that we can. And what we've presented today is a way of combining these and taking the best of both worlds to be able to still take advantage of all these same properties while also scaling. Thanks.
So we have time for a couple questions. So I have one question. So what is the intuition for like the type of graph that will screw up your method the most? Like, is there something that would cause it to only stay in the sampling stage and never jump to the exact inference stage?
So a very densely connected graph will cause it to spend a lot of time on sampling.
Okay.
If you pick the right type of heuristic for that graph, you can still do very well because you are a sampler. And one of those example benchmarks is basically a completely connected bipartite graph.
Yeah.
But yeah, it does depend a lot on the combination of how the graph looks and what heuristic you're picking. Yeah.
Great. Thanks. Any other questions? Please.
So you talked about sampling using a distribution from the circuit you've constructed so far. Mm-hmm. What about all the variables that you haven't added to the circuit yet? Don't they influence the marginal? Yeah,
they can influence the marginal, and it's not the exact marginal distribution for that variable. It's just in general we found that it's a very good approximation, especially once you get kind of a little further into the process. So at the beginning, it can kind of struggle sometimes, which, one way to kind of improve this is to take a baseline proposal distribution that you can use at the beginning. But once you get sort of further into the sampling procedure and you've considered a lot of variables, we found that that proposal is actually pretty good.
Oh, so there's a proposal, and then but the importance weighting you do need in order to get the right answer in the end. You do need the influence of all those other variables?
Yeah, so when you compute the importance weight, you need to consider what you need the exact distribution, but of the combined proposal, not the, you only need a unnormalized version of the true distribution, and you get that at the end from the circuit that you have left.
Thanks.
Okay, let's thank the speaker.